All right, chapter 17 in the Klein textbook. Everybody? No, we can fit in a couple minutes here. I got to fit this in order to stay on schedule. So chapter 17 is on conjugated pi systems. This won't be anything new. It's just going to be an introduction to things we've already seen before. We just really didn't know what to call them. So the idea of a conjugated system is a pretty easy one. A conjugated system is alternating double single bonds. Oh, sorry, my pen changed. Oh, black, medium. All right. So if we think about a conjugated system, we could say that this is a conjugated system, right? It's alternating double single bonds. There's another system that's closely related called cumulated, and that dot in the center is just used to describe a carbon. So it's actually adjacent carbon-carbon bonds that are head-on attached to one another. And then there's another one that's also similar to these, and this is called isolated. So we've got conjugated, we've got cumulated, and then we've got isolated. In both cases, we've got two pi bonds. It just has to do with their relative positioning to one another. So in this case, conjugated systems are always going to be a single bond apart, not more than one single bond. Like the isolated case, we've got two sigma bonds apart. So let's take an example here. This is an example that somebody was asking me in my office hours about IR. Let's take this aldehyde versus this aldehyde. Which one is conjugated, the one on the left or the right? The left. We've got alternating double single bonds in it, right? So if we look at this one, we can say, all right, it has a resonance structure where the oxygen has a negative charge, the carbon has a positive charge, and the double bond remains in place. Or we can even have it more delocalized. Excuse you. And the positive charge is down here. So conjugated systems are pretty unique because there's a lot of resonance delocalization, where in this one, we can't move that pi bond. We can only have one resonance structure where there's an oxygen with a negative charge and a carbon with a positive. So in this example that I gave you, this one's conjugated. This one is isolated. And it's because of this delocalization that we can observe a variety of really unique reactivities because of all the different possible resonance structures. So one thing I wanted you guys to do on the problem of the day that I just handed out was to go through a mechanism that we've already seen and then see if there's any sort of delocalization and see if you might even get more than one product out for each reaction instead of just one product. So I want you guys to try to troubleshoot this a little bit on your own, but try to think about what can stabilize a carbocation. It should be pretty simple at this point. The neat thing with this is let's kind of take a look at what's going on in a conjugated system. I'm not going to include hydrogens. I'm just going to include the carbon backbone. So let's say we've got this carbon backbone, and it's all sp2 hybridized, like in our conjugated system. If we think about it, all of these carbons have p orbitals, right? Not the greatest looking p orbitals. But in either case, we can have a pi bond between the end pieces, or we can conversely have a resonance structure where that pi bond is now delocalized and we actually have some double bond-like character in between the internal carbons. So now there's a pi bond more on the center carbon rather than the exterior carbons. This makes this carbon-carbon bond pretty weird, because if we look at it in the way we normally draw it, we draw it as a single bond, but is it really a single bond? No, it has double bond-like character, right? So if we look at this carbon-carbon bond, it has double bond bond-like character. So this gets interesting to think about. So let's take this system and draw it out a little bit lower. So I'm going to take this diene. Actually, let me slide it over a little bit. It's a diene because it's got two alkenes on it. We can apply energy to this, and we can actually get that single bond to rotate that I just said has some double bond-like character, and we actually call these by different names. This is called an S-trans diene because that single bond is acting like a little bit of a double bond, so the groups are trans to one another. The one on the right is going to be the S-cis diene. And it actually takes a fair amount of energy to knock this into the S-cis conformation because we know that cis, we run into steric repulsion. So it's energetically destabilizing to go to the S-cis. And it's about 15 kilojoules per mole. The interesting thing about this is the S-cis diene is less stable, but it is more reactive. And I think that's where we're going to leave it today. We're going to study a lot of reactions with this S-cis conformation, where we've got a diene where they're both facing each other, and we're going to learn a really cool reaction called the Diels-Alder reaction, where this is a very powerful way of making carbon-carbon single bonds. All right, I'll see you guys tomorrow.